stream. All right. So today we're going to do some more with programming efficiency, and I don't know like what shows up on your YouTube feeds, but my YouTube feeds are scattered with computer science and playlists of study music. So one of my favorite channels is fireship.io, and they do have a series called Blank in 100 Seconds. So it essentially describes some sort of computer science topic in 100 seconds. So let's use that. They're actually really funny if you really pay close attention to what some of the things they do. So let's review Big O notation using this little video right here.
Performs as its input size grows.
It goes quick.
As we add more inputs or data points to an algorithm, there are two things that might grow in complexity. It may take longer to run the algorithm, which we call time complexity, or it may require more memory, which we call space complexity. The variable n represents the number of inputs. Now imagine n being scaled up to infinity. The faster the result grows after each step, the worse your algorithm performs. In technical interviews, you'll often be asked to estimate the time or space complexity of the code you've implemented. Take, for example, a loop over an array of elements. It takes exactly 1 unit of time to loop over each element. This is known as linear complexity, because we have a perfect one-to-one relationship between the number of inputs and the amount of time it takes to execute the algorithm. But we can often do better than linear time. If we have a sorted array, we can implement a binary search, where we start in the middle and then jump back and forth until we find the actual value we're looking for. This is known as logarithmic complexity, and it scales much better to a large number of inputs. At the most efficient end of the spectrum, we have constant time. An example is looking up an element in an array by its index. No matter how big that array is, it should always take the same amount of time. But things can also get less efficient. Imagine a loop within a loop. This is quadratic complexity, where the number of inputs is raised to the power of 2. And things can still get worse with exponential complexity. Imagine looping over every possible combination in an array. Some algorithms may have multiple different growth rates of complexity. Always simplify your notation down to the fastest growing worst case scenario. This has been Big O notation in 100 seconds. Thanks for watching, and I will see you in the next one.
All right, so yeah, that should be a quick recap of what we did in about 50 minutes last class and about 100 seconds right there. So like today, again, is going to be quite a bit more practice. So one thing that we'll want to keep in mind is the ordering of the running times. So let's go ahead and start off with a little bit of an exercise right here. We looked at 6 very common running times: polylogarithmic, constant, exponential, polynomial, logarithmic, and linear. And what we want to go ahead and order those is from fastest to slowest. So let's go ahead and start this one off together. Of those 6 running times, what one would be the fastest for a large input? Constant. So again, constant would be the fastest, and of course, we typically denote that as big O of 1. So with that being said, let's skip a few. What would be the slowest, or what one would take the most amount of time for a large input? Anyone other than Anna? Exponential would be the slowest. So that was my question. Maybe you didn't catch that one. So the slowest of these is exponential, which would be like big O of c to the n, where c is some constant. So go ahead and consider the other ones. Go ahead and maybe take about maybe 30 seconds. Ask your neighbor, hey, which one do you think comes next? Let me give you 30 seconds to see if you could order the other ones. And if you're not sure, there's a link to a cheat sheet, so feel free to cheat if you need to. So let me give you a moment there. All right. Once you got your answer, go ahead and check it, and then we'll go over it together. Multiplied. Yes, it's the product between a polynomial. Typically, like a linear polynomial was kind of the most common one, which we'll look at more next week. But yeah, polylogarithmic is n log n. So the order right here, constant, of course, is ideal. Then your next goal would be logarithmic. Logarithmic time complexity is still very, very good, especially if you kind of were following that little illustration they had in this video right here. Let me find it. Yeah, like if you look at this, look at how slow the logarithmic time complexity grows, especially compared to the linear or the polynomial. You can see this is blowing up, and this is very slowly ticking. Especially if you think about it, like once you get like to powers of 10, like you have to increase a logarithmic function by 1, you have to increase by a whole order of magnitude. So to go from like, if you think about it, if you were looking at like base 10, to get from a number from 6 to 7, you would have to go from 100,000 to 1,000,000. You would have to increase by 900,000 just to go ahead and increase a logarithmic function by 1 unit. They're very slow growing functions. So again, that is why logarithmic is next. Of course, then a linear is following that one because again, it is a 1-to-1 increase. And of course, logarithmic for large numbers is greater than 1. So if you think about it in terms of a vertical kind of stretching or just multiplication, polylogarithmic or log linear is also sometimes if you're focusing on the actually being n. But polylogarithmic is a little bit slower. So that's big O of n log n. Again, if you kind of look at, of course, if you multiply two whole numbers, you're going to get something that's larger, so that makes sense there. And then, of course, logarithms are, if you think about this as like logarithm is smaller than a polynomial or a linear, so that would mean that your polynomial time would be next. And of course, if you are really inefficient, you'll end up with an exponential. Exponential, we'll look at some examples of that today. Exponential shows up also with like permutations. If you were to try and find all the permutations of a set, it's very hard to go ahead and get all of those different arrangements. The problems grow large. So make sure you're comfortable with those. And if you needed to cheat, you can always go to cheatsheet.com, and that has that same graphic that shows the actual graph of these. And again, you don't ever worry about negative operations because we're talking about time. So like our negative elements, because you aren't going to have negative elements. That's weird. And something that we've talked a little bit about this course, but basically the main one that we work with are like an array with Python. That's like kind of like Python's list. Python's list is a little bit fancier than an array, but you can see like some of the operations, like accessing array is constant time, searching an array, which is linear time. But again, this is more of the array in like C or Java. Python's list is a little bit fancier. I think it's closer to, it's actually using a little bit of a linked list kind of idea. Anyway, we didn't talk too much about data structures. We're going to talk about sorting algorithms next week. We're not going to go through all of these. And if you really just are loving this, you can buy a poster. I mean, you can go ahead and get a $37 poster and hang it up. Nerds, I'm just kidding. I really kind of want that poster. It looks super cool. Anyway, that's a little bit of a review from last time. Does anyone have any questions from that? Okay. Yeah, Anna.
Could you explain the video shows like log n equals 9? What is it showing?
Where at?
So
The Worcester algorithm.
what is the answer?
Okay, so basically they're considering like this right here as your input, and like if you were to plug in like, again, this is log base 2 in computer science, so you can see like 8,000 right here. If you were to plug that in here, you would get approximately 9. If you were to plug it into a linear function, it's 1-to-1, so you see right there. And if you were to square 8,300, then you end up this right here. So it's just, this, of course, big O is, remember, the worst case scenario, like how long would it take to run? If you were to like, suppose you were searching a list and your list was 8,303 elements long, in an algorithm that was log of n time complexity would take about 9 units of time. In a linear algorithm, like a linear search, it would take 8,300 units of time. And if you, somehow you wrote a search algorithm that was n polynomial, which please don't, because I mean, if the dumbest way to search a list is one element at a time.
Right.
So if you did something to make it a polynomial, you're just playing at that point. So, but yeah, does that answer your question?
Yes, thank you.
Yeah, as the problem size grows, you want to write an algorithm that, of course, is as small as possible in terms of big O notation. All right, so today, again, that's going to be a little bit more, our goal is to just work with some more examples. So the law of addition basically said you could take the sum of big, like, it's just, I'll write it like this. It's like, for those of you taking abstract algebra, it's like a homomorphism, that if you have two functions that have their own different time complexity, so like if you have big O of f of n and you have big O of g of n, you can go ahead and just consider big O of f of n plus g of n. And this is does anyone remember when this occurred? This first problem is just a review. This is when we're considering what type of statements. Cool, y'all reviewed. Sequential statements. So again, if you think about this, if we look at this linear search down here below, this first statement here was big O of 1. It was just to assign a variable to a someplace in memory, and you assign it some value. This part right here was the search. This was big O of the length of L because we iterated through here. And if you look at each thing inside here, it's just going to be a constant number of operations. So we even talked about the law of multiplication, which comes whenever, I meant to say blank here, not black, but this is whenever we're looking at like nested statements or nested loops. So you can see right here we have nesting inside of this loop. So this was constant time. This was also constant time. So, and then again, the returning is of constant time. So if you look at each line has some time complexity, and then if you think about here, let's just make things simple. Let's let n equal to the length of L. So this right here is actually just big O of n. Is everyone okay with that? That I just say n is the length of the list. So you have the multiplication rule right here. So you have n times 1, which is just still big O of n. And then you have the addition law basically says this the algorithm's time complexity is, well, it would be big O of basically 2n because we're multiplying inside, plus 2 because we're adding these out here. But of course, remember big O, we kind of collapse it down to the dominant term. So what would big O of 2n plus 2 simplify to in terms of what would the big O allow us to write this as? Big O of anyone? N. It's just a linear time algorithm. So those were how the rules played out. And of course, the video touched on it, but list access by index is big O of 1. And Anna, I think, asked that question at the end of last class. The reason that is because it's just doing it by some mathematical formula, and mathematic operations are constant time, so list access is constant time. And Python, the length lookup is also constant time. There's some fancy things happening under the hood that means it doesn't matter whether the list is size 1 or 15 billion. At some point you run out of memory in your computer, so that's a different idea. But those are constant. Yeah.
How did you get 2n plus 2?
Because the nested statements right here, law of multiplication says I'm going to go ahead and multiply this with all of the constant statements in right here. So if you think about doing two constant statements, there's 2 steps. How many times are you going to do that? N times. So if you do what if you think about it like this, you do 2 things n times. How many times did you do it? 2n.
So would it not be like, because the only time that because I'm confused because the only time that it would do the second step is when E is equal to the first step.
Fair enough. Again, that also does. So some of this does depend on the actual type of the problem.
Okay.
So it could be a list where they're all the same element. So and that's the worst case scenario, and it would find it every single time. So worst case scenario, both of these would run. So let me pose that question because that was a really good question. The question is wait, how many times is this going to run? Remember, Big O deals with worst case scenario. So the worst case scenario is this would run every time, and you can imagine it would be basically L is all E. Let's say E is equal to 1, and you're searching for E equal to 1. It would run true every time. Now, of course, we talked about this a little last class. The smarter thing to do would be then to break here. Then you wouldn't have to do that, but asymptotically, it's still worst case scenario. Does that help?
Okay,
Yeah. Sure. Any other questions about this first one? All right. Yeah, you're can I go back to writing programs? And again, we've covered a lot of the ground. So this is kind of the analytical part of it. So example 2, we have a product right here. So let's look at this algorithm and think about what it does. It computes the product of two numbers. Remember, a product is just a repeated sum. So you could think about this kind of in the same way as we did above. The assignment's big O of 1. This is running big O of B times, where B is going to be some integer right here. This, of course, is going to be, does anyone remember what basically is big O of 1, but how many steps actually occurred when you did this? 2. Very good, Caroline. You have the actual assignment and you have the addition. Because again, so this is actually 2 steps because sum is equal to itself plus A. So again, you have the summing, and then you have the reassignment back to sum. And of course, this is also constant. So to return as a constant operation. So you can see each step does have its kind of own time complexity, its own cost. And of course, then you really are just focusing on the thing that is the bottleneck. That is why we collapsed the addition. So does anyone remember what the time complexity of this little algorithm would be? It's big O of B. It's linear. Again, it's linear in terms of B this time because we're not, you could say N, but then you would adjust that up there, but that's big O of B. So there's another example. All right. So those were ones we looked at last time. So now maybe that you aren't trying to recall what we did last time, we'll do some from fresh. So here we have an algorithm that determines if one list is a subset of a second list. So it has two inputs, list 1, list 2. And what it's going to do is for each element in the first list, it's going to initially set it to false. And it's going to then iterate through the second list, the elements in the second list. And if it finds that that element is the same, it will go ahead and match, and it will go ahead and break. But if it does not match, it'll return early because, again, remember, what does it mean for one element to be a subset of another? So like if you have list 1 is, let's say 1 and 2, and list 2 is 1, 2, 4, sure. You can see right here, this should return true because list 1 is a subset of list 2. So with that in mind, take a moment and think about what would be the time complexity of this one. Feel free to ask your neighbor if you have no clue. You may want to remember how nested statements work, or nested loops. Let me give you maybe a minute here. All right, let's see what y'all come up with. Anyone have any ideas? You don't even have to give me a fancy function yet. Just kind of think of the classes. What would you all say? Would it be constant? Let's do it this way. Anyone think this is constant? Good. The constant ones are pretty rare. Let's go in order. So what comes after constant? Logarithmic. Anyone think this is a logarithmic time algorithm? Good. No, it is not. And we'll talk a little bit more about logarithmic time complexity, but logarithmic time complexity simply occurs when you're dividing the problem in half each step. If you look at this, there's no real it's not like we're dividing the list in half each step. Okay, so what comes next? Constant, logarithmic, then we had linear. Would you say this is linear? No, I see you shaking. I see a couple of you shake your head. No, it would be if there was maybe only one iteration through. Okay, so would you say this is polylogarithmic? Is there kind of a part of the problem that's being divided in half each time? No. Is this polynomial? I got a hesitant yes. This is a polynomial time algorithm. It's actually a quadratic time algorithm. The main thing to keep in mind is that we're looping through two things right here. So let me go ahead and highlight those two lines. Oops, highlighted the wrong one there, missed. Let's try that again. Anytime you have nested loops, this is a good indication that you're looking at some sort of polynomial or polylogarithmic time algorithm. So if you think about this, the amount of work that's happening is you're going to have to iterate through each element of L1, and while for the first time, when you're stuck at 1, you have to go through all of those right there. And same thing, when you do 2, you have to go through all of the second ones over here. So this algorithmic is actually polynomial, more specific. It is polynomial, more specific. It is actually a quadratic time algorithm. But let's think about what is it in terms of the actual input. Now, we do have some things we could go ahead and consider, for example, L1 or L2, which one's larger? So we can maybe make an assumption that one is larger than the other. So you really could do something like this is big O of the max of the length of L1 and L2. Time and you'll go ahead and then square that, but we can maybe make a simplifying assumption and just say L1 is the larger list. And actually, now that I'm looking at this algorithm and just kind of thinking about it, this one does assume that L1 is the largest one. So this one, the following algorithm determines, I should say this, if list 1 is a subset. Or let me think about this. For each in L1, start false. For each in L2, this algorithm, again, I would want to play with it a little bit more. This algorithm determines if L2 is a subset of L1, I believe. I'd have to play with this one a little bit more. Just as I stand in front of you and try to talk about it, I have more thoughts in my head about that. Y'all know how that goes. Those of you who tutor, and I think pretty much every math major tutors at some point, whether officially or not, as you explain things. So so to simplify this is actually big O of length of L1 squared. So it is a quadratic. Worst case, they're the same size, because what's the worst case when you're considering subsets? When they're the exact same subset. So the worst case would be if this was 1, 2, 3, 4, and this was also 1, 2, 3, 4. It would have to iterate through both of them completely for it, because what's going to take the most time when one subset when they're the same set. Because a subset is a subset of itself, or a set is a subset of itself, which is a good thing to remember because we're talking about power sets in a few minutes. Discrete flashbacks, anyone? All right. So let's look at this next one. I talked about this a little bit last class. If you haven't done, is there anyone who's never worked with matrix before? Okay, so just to expose you to it, and if you haven't done it in a while, quick thing to remember about multiplying matrices is it is a lot of effort. And when you all take linear, I have a feeling you may try to just write a program to do it instead of doing it by hand. For those of you who already took linear, you had a great time, I know. But essentially, the way that you multiply matrices is you basically take combinations of the first row with the first column, and then you multiply them together, and then you add them, and all of that work to get you one entry of the product of the resulting matrix. So the matrix multiplication is actually a very time-consuming algorithm, and I actually have the algorithm in the notes. You may want to play with it, but you can see if you have this 3x3 matrix, and there are certain assumptions, like you have to have the number of columns in the first matrix must match the number of rows in the second matrix. It's also a non-commutative operation, but anyway, we're kind of outside of the scope of what we're doing right here, but this would be the dot product. So this right here is the algorithm to multiply them, and some of you, if you kind of think about this, might be able to kind of see what is happening when you did it by hand, but just kind of looking at the structure of what this is, what this algorithm looks like, what do you say is its time complexity? Look through that again. Okay. It's polynomial. So whenever you have nesting, so if you think about this, let's look at what we have. We have a nesting right here. An exponential would occur basically, and we're going to look at an example of an exponential later, is essentially when the problem is going to explode as you do more. So like what if like one of these steps created another whole matrix that you then have to multiply in? I'm just kind of throwing something out there. But typically an exponential algorithm creates new data that you have to deal with. So this one, if you look at this, we have a nesting of 3 loops. And if you, let's just basically assume maybe that every one of these is like the same size. So you basically have like big O of n, and then you have linear amount of work in each, let's just think about it. You have linear amount of work in each step. And obviously like the worst case is, of course, everything would be like as big as possible. But if you do n things n times, and while you're doing those n times, you're doing something else n more times, you actually have something that is cubic in nature. Yeah, Elena.
So for exponential, it would be like you had a constant, and then that constant created a function.
We'll look at an example down below. Yeah. So basically, you create more things. This again is still a fairly simple computation. It's just you have a lot to do. So this right here that was correct. This is a cubic or a polynomial time algorithm right here. Now, here's kind of an interesting idea. The world pretty much lives on matrices now. Like all of this big, like if you guys watch any sort of like tech channel or something like machine learning this, your computer knows when you're going to be doing this. And basically it is just a massive like array, a massive matrix, and it's just doing computations on this. So this is, if you remember, like, is this a good algorithm? Like n cubed is that fast? You could remember back to our chart, or where was our cheat sheet? Where was it? Up at the top? If you look at this, polynomial time algorithms are horrible. Like n squared is horrible, so n cubed is even worse. And we're not going to it probably is. You probably could understand it, and I'm not going to sell you all short. You're all really smart. But there was a computer scientist and mathematician named Strawson, and he actually does a clever thing where he reduces the size of the problem and looks at certain properties of the matrix. And he actually was able to reduce this. It's still polynomial, but let me see. I wrote it down here. It's kind of a funny one. He got it down to an n, and then it was log to the log 7. So this is about approximately n to the 2.807, and it goes on, obviously logarithmic of a non-square. but it doesn't look like it much. But when you're dealing with data sets the size of Google, that's a little bit of an increase is very clever and saves millions of dollars. From a computational standpoint. So the Strawson's algorithm does essentially some divide and conquer to simplify this. And there's also other tricks like partitioning. I don't know, how many took linear already? So 2 of you, so like you look at a partition matrix and things like that. But we're not going to talk, you could Google it if you're interested. It does a clever divide and conquer thing right there. Okay, so how about a nested, let's look at another example, speaking of nesting. Let's see if you guys are kind of catching on with what's happening right here. So take a look at this example. It's a very kind of contrived algorithm right here. It's just G of n takes some non-negative input and it loops up to n, and then it adds essentially from the range, and technically to make this appropriate, we should make this we should also call that an int, because of course log base 2 is going to return some float, so let's cast that to an int so that we can call range on that, because range, remember, needs an int. So take a moment, what do you think the running time of this one is? What is, here, ask your neighbor. Well, you all right, Bailey? You take us? Okay. All right. So ask your neighbor, what do they say? Oh. All right. Anyone think they know?
Kenneth said polylogarithmic.
Kenneth? Oh, I get it. It was a joke. Yeah. I was like, you texting him in the middle of class? I'm like, he's not here. I get it. That was funny. I enjoyed that. How many say polylogarithmic? Yes, everyone agrees with Kenneth. He's going to have a great time listening to this video later, won't he? But yeah, that's correct. Of course, if you have a linear amount of work right here, so you see you have like big O of n, that's a function of the input n, but this is also a function of n. It's just not near as big. So again, you have the idea of the multiplication rule that this inner loop is log n, the outer loop is log n, the inner loop is, I keep saying this backwards, the outer loop is big O of n, the inner loop is logarithmic, so their product, of course, is n log n. So very good. So maybe to emphasize the idea of what is happening when you're looking at a logarithmic algorithm, we saw one earlier in the semester when we did the bisection search or binary search. But to recap that, I have another binary search in 100 seconds, and they must have known that we were doing this because this one came out like 4 days ago. So let's go ahead and pull this up and just remember how binary search works. So let's go.
Finding an element in a sorted array by continuously chopping the search area in half. The first known implementation took place around 200 BC in ancient Babylon on clay tablets used for record keeping. But your brain has likely implemented binary search in everyday life without you even knowing it. Imagine looking for a word like magic in the dictionary. You wouldn't flip every page until you get to M. Instead, you open it in the middle. If you overshoot to the Q's, then you go to the middle of that chunk. This time you undershoot to the J's, so you do the same thing again, but in the other direction, until finally you find the page you're looking for. Easy enough. Now it's time for your technical interview. You might be given a question like, given a sorted array, write a function that returns the index or the given element. The easy way to solve that problem is with a simple for loop. Just loop over every element in the array until you find the one you're looking for. That works, but you fail the interview because you need to go faster. A regular loop results in linear time complexity, but you can do better than that. Here's how we might map out a binary search on a whiteboard. First, we need to figure out the middle index. Instead of starting at index 0, we start in the the middle. If it's equal to the target, then we return that index. But if that element is greater than the target, we know the target must be somewhere on the left. So we find the middle of that slice of the array. But if it's less than the target, then we know the target is somewhere on the right. So we repeat the process for that slice of the array. The result is a much faster algorithm with logarithmic time complexity because it's able to divide and conquer. Now, to implement the code, we could use an iterative approach with a while loop or a recursive function. Either way is acceptable, but let's define a recursive function in JavaScript. The function takes the target value as an argument, as well as a starting and ending index. First, we have a base condition to stop looping when it reaches the end of the array, at which point we know the target is not in the array. From there, we compute the middle index, then we check to see if that middle index is equal to the target, at which point we can return because we found the element we're looking for. Otherwise, we need to continue searching, and that's where recursion comes into play. If the middle value is greater than the target, then we'll call the same function, but this time we'll put the ending index at the middle. The other possibility is that the middle value is less than the target, in which case we can also recurse, but this time we'll put the starting index in the middle. And now we have an algorithm that can find an element in a sorted array much faster than a regular loop. If you want to see more videos about algorithms on this channel, hit the like button and let me know in the comments. Thanks for watching, and I will see you in the next one.
Anyway, great channel. Unity in 100 seconds, yes please. Well, no, can't right now. Anyway, definitely feel free to explore more on that channel. So anyway, that was we looked at binary search, and if you look at this code, this is very similar to how you might have implemented it earlier in the semester. So if you look at it, let me just kind of highlight this. There's two different ways. There is a recursive method. You can see the recursion right here. Let me highlight that. So that's where your recursive step is happening. And then of course you have basically your base case being checked right here. Now, if you look at this right here, you have low and then you have mid, and it's essentially just kind of passing in the indices for the high and the low. So basically what's happening at each step of the recursion, you're looking at the array of half the size. So that is what kind of the indicator of something that is logarithmic, when you go ahead and consider something that is doing it by half the size, with a caveat. So I'll go ahead and say that down below. So an iterative implementation is kind of the same thing. I think when we did it iteratively because we didn't have recursion yet. But again, there's the recursion algorithm. But iteratively, you can see right here, you basically will just update. This is where you're essentially doing the same logic. You're just updating either the low or the high, but notice you're cutting the problem in half. So you saw this in the video, but if you were to search for F using a binary search, this is what you'd want to do. So the first step, you would divide the problem and you'd have E, F, G, and H. Then you would have to go ahead and just use E and F. And then finally, you would find it at F. So if you look at this, we have 8 elements. And how many steps did it take us to find it? Well, don't count your first step. That's just it. Took you 3 steps. What is log base 2 of 8? 3, right? So that is kind of a concrete example. So we have basically step 1, 2, 3, and then again, notice log base. And again, in programming and in computer science, typically log when non-specified is 2. So log base 8 of the n elements is going to be equal to 3. And notice that's how many steps it took us here. So the complexity here is log of n. So logarithmic time complexity occurs. Let's go ahead and put this in Word. When the problem size is halved each time through the process. Now this is kind of like using the idea of base 2. And let's go ahead and look at the next example. Any questions on that one right there? This is just like a flyby. I would encourage you to code up these algorithms and play with them yourself just to get a better understanding of them. So let's look at one more today, and then we'll probably save the exponential one for Monday, but I'll maybe just say a few brief words. So take a look at this one. Think about what this algorithm does. Go and read through it a couple times and kind of maybe highlight what you're doing, and maybe answer the question, how many times can I be divided by 10? So So go and take a moment and look at that. So it is an iterative algorithm, hence we see while I is greater than 0. Did anyone kind of catch what this algorithm is doing? The page tells you if you weren't sure. It just casts an integer to a string. So earlier in the semester where you had to basically do like maybe you had str of 1 and you want to concatenate that, and you do str of 2, and then this is going to give you 1, 2. That's all this does. So Python has a function that allows you to cast it, but how is that actually implemented? So this is maybe an algorithm that implements that actual casting function under the hood. Python is open source. You can actually you can go through all of the source code for it and probably find how they implemented it if you're curious. I've played around looking through their source code. It is a labyrinth, but it is fun. But anyway, so anyone think they know? Here, let's answer this question. Let's make it a little more concrete. Let's say I is equal to 12. How many times can you divide I by 10 and still have something significant? So if you divide, so let's divide it. So if we do 12 divided by, and again, let's divided by, and you can see it's using integer division here. So 12 divided by 10 is going to be 1. And then 1 divided by 10 is going to be 0. So there were 2 divisions before we hit the trivial case. And you can see right here, while I is greater than 0. So again, we would have done 2 divisions, right? So what if we were to do I is equal to 123? How many divisions there? How many times could you divide 123? Yeah, there's 3 divisions here. So if you think about this, we increased by an order of magnitude, but how much more work did our algorithm have to do? 1 step. So what is the time complexity here? You increase by an order of magnitude, but so basically, if you increased, it's not linear, because it would be linear if you went from 12 to 123. What was the increase between 12 and 123? So what would be 12? That is 100 and, wow, help me here. 12, right? No, 11. No one saw that. It's recorded. Dang. Anyway, the difference is 111. So you increase the input by 111. Did the time increase by 111? No, that would be a sign of a linear algorithm. One that when you increase it by 111, the time increases by 111. That's what it means to be linear. So we increased by an order of magnitude, a power of 10, and we got 1 more. What type of function, when you increase it by a power of 10, increases by 1? Log base 10. So this is actually a log base 10 of n. Of course, you would still typically call it logarithmic, because log base 2 and log base 10 grow pretty close to each other. But anyway, that's right there. So we increase our order of magnitude. This time we didn't have the problem, but when we increase the problem by quite a bit and the algorithm just takes a little more work, is also another type of logarithmic scenario. So any questions on this one? By the way, do y'all remember what a power set is? So I'm going to leave you a little bit of a challenge for this weekend, since many of you are finishing up. So here's your unofficial homework problem. Given a set of unique integers, generate the power set. The power set is the set of all subsets. So, if you let's consider 2, you have a set of 2. What are some subsets of the set 1, 2? The set of only 1, the set of only 2, the null set. I'm glad someone said that. Yeah. And what was the last one? The set that is itself. So the power set is the set of all subsets, and typically you would order them by cardinality. So let's go ahead and just put that one first. And does anyone remember the size of the power set? Like if basically, let's say the cardinality of L is, let's say n, then the cardinality of the power set of L, does anyone remember? It would be 2 to the n. So this is, of course, where we're generating more work each side. So what I'm going to say is kind of an unofficial like homework problem for the weekend. Maybe do like generate some different power sets just to maybe get that problem back in your mind, just to remember what a power set is. And we'll look at an algorithm and why it would be an exponential time complexity algorithm. We'll review it, and then we'll probably next week talk about some searching algorithms. No, we talked about sorting algorithms, because it's nice if you could sort then search, because then you actually know where you are relative to the other elements. But any questions? Okay, if you do have any homework questions or whatnot, feel free to stick around. Otherwise, enjoy your weekend.